Ladies and gentlemen, dear students, my name is Stefan Rahmstorf. I am head of the Department for Earth System Analysis at the Potsdam Institute for Climate Impact Research in Potsdam in Germany, and I will present you Lecture 3 from a series about the report of the German Advisory Council on Global Change called World in Transition: A Social Contract for Sustainability. And Lecture 3 will deal with climate change and the impacts of climate change. The first episode will be about the basic facts about global warming, whereas the second episode will be about the impacts of climate change and mitigating climate change. We will start with the first episode, and there you will understand the fundamental role played by the Earth's energy budget in setting the global average temperature and understand how this energy budget works. You will understand how global temperature has increased in the last 100 years and which change in the Earth's energy budget is responsible for this warming. And you will also understand how future changes in greenhouse gas concentrations will affect the global temperature. So the contents of this lecture is, first of all, the Earth's energy balance, second, the rise of the carbon dioxide concentration, changes in global temperature as we observe them, loss of glaciers and sea ice, and scenarios for future warming. We will start with a very simple basic fact, namely our Earth's energy balance. The energy that drives the climate system comes from the sun. And the sun, of course, radiates energy in all directions into space, including in the direction of the Earth. And about 1/3 of the radiation that arrives at the outer perimeter of the atmosphere of our planet is reflected back into space, mostly by the bright surfaces, the cloud tops, or the snow and ice surfaces of the planet. And the Earth itself also, like any physical body, radiates energy into space. In that case, that is long-wave radiation according to its temperature. And you now already see on the slide that this results in a very simple energy balance, namely that the incoming solar radiation minus the part reflected straight back into space must equal, to very good approximation, the outgoing radiation emitted by the Earth into space. This is a very fundamental energy balance, the first law of thermodynamics, and any sustained sizable change in the global average temperature can only be driven by either of these three factors, either a change in the incoming solar radiation, which we call insolation, or a change in the percentage that is reflected into space. We can do that, for example, by changing the brightness of the Earth's surface, by cutting down forests and replacing them with agricultural lands. Or the third possibility is that we interfere with the long-wave radiation into space. That can be done because that radiation has to go through the atmosphere to be able to be emitted into space. And in the atmosphere there are certain gases that intercept this radiation and thereby make it harder for the Earth to get rid of the energy that is streaming in all the time from the sun. And we will see that all these three possibilities have played a role in the history of Earth's climate. And when we're looking at certain climate change, we always have to look at which of these factors is actually changing and is responsible for the change in global temperature. Now we can look at this radiation balance in a bit more detail in the energy budget. Here we see a detailed picture which you don't need to understand now in all the details, but at the top of the atmosphere you see that simple radiation budget that I just explained, with the incoming solar radiation in the middle coming in, the reflected part on the left. And on the right-hand side, at the top of the atmosphere, you see the long-wave radiation leaving. Now, if you look at the budget at the Earth's surface, it looks rather different. Again, you have a part of incoming solar radiation that reaches the surface, but on the right-hand side there, you see a big, very thick arrow of the outgoing long-wave radiation. But you also see on the far right an arrow coming back down from the atmosphere. That is the part of the long-wave radiation that is intercepted on the way out and is radiated back to the Earth's surface. And this downward radiation is what is causing the greenhouse effect. A totally natural effect, of course, that exists already since the beginning of the Earth and is what is responsible for making this planet habitable in the first place. Without greenhouse effect, it would be far too cold. The Earth would be totally frozen over and no life would exist. And we will see in a minute that human activities are now changing the magnitude of this greenhouse effect in a way that causes the surface temperatures of the Earth to change. You can see here also that this back radiation received from the atmosphere, radiated back down to the surface from the atmosphere, is actually larger than the solar radiation that we receive at the Earth's surface. So this is not some small thing. It's a very major component of the energy balance at the surface of our planet. And by the way, it's also a measured fact. All these numbers in the radiation budget, they can be measured. On the top of the atmosphere balance is measured by satellite missions, and to measure the radiation at the Earth's surface, there is a global monitoring network, radiation monitoring network. I mentioned earlier that all three reasons for changes in global temperature have played a role in the past, and here is one example: the ice ages that probably all of you have learned about in school. The Earth has gone through a series of ice ages caused by changes in the Earth's orbit around the Sun. So in this instance, it is actually changes in the solar radiation received at the Earth, which have caused the climate to change in a cyclical fashion with dominating period of 100,000 years. And the blue curve shows the variation in carbon dioxide concentration in the planet's atmosphere. The red curve shows the temperature in Antarctica during 4 of those cycles over 400,000 years. And you see that although the driving force here is a kind of sinusoidal cycle, the resulting climate change has more of a sawtooth pattern. Now, why do I show this? One reason is to put the modern changes in carbon dioxide concentration into a long-term context. In the last 400,000 years, as you can see here, the CO2 concentration in our atmosphere has varied between 190 and 290 parts per million. And what now has happened in the last 100 years is seen here. In the meantime, the CO2 concentration has increased to 390 parts per million. So it's more than 1/3 higher, actually about 40% higher than it has been at any time in at least the last 400,000 years. But as we know from further ice cores, in the latest one being by the European Ipcc project, we know that this is also true for the last almost 1 million years. The result the second reason why I show these ice ages is because we use the ice ages to test our models. We use the models to simulate ice ages, and here you can see a view of the continental ice masses on the northern hemisphere, which grow and shrink in the rhythm of these ice ages. And this is you can see that they increase and decrease according to these orbital cycles. And we compare these simulations that are driven by the orbital cycles and also by the up and down of CO2 in this case. We compare those in detail with the geological data that we have where the ice actually was. And we find there is a pretty good agreement in what the model predicts and what the geological data tell us about the ice ages. And in those places where there is still disagreements, of course, that's the most interesting part to us, because there we learn where there are still deficits, where we can improve the climate models and so on. Here we zoom into the last 10,000 years of CO2 measurements. They are from the ice cores in Antarctica, and this diagram very clearly illustrates the massive increase in the last 100 years or so. And note the additional feature on the right-hand side. There is a scale in radiative forcing in watts per square meter of Earth's surface. And this scale shows us how much the Earth radiation budget, that very fundamental property of our planet, has been changed by this increase in carbon dioxide. There is an extra heating rate of 1.7 watts per square meters of Earth's surface implied by this increase in CO2 concentration. Now we know that this rise in the carbon dioxide concentration is completely caused by human activities, and we're very certain of that. And there are two reasons for this. The first one is that the isotope composition of this additional carbon in the atmosphere gives this away, because fossil carbon has a different isotope composition. And so already in the 1960s, it was shown that this increase is due to fossil carbon that has come from fossil fuels. But there is a much simpler reason as well, and that is, if we just do the sums, how much CO2 have we emitted from fossil sources? We know how much coal, how much natural gas, how much oil we have dug up from the Earth's crust, and so we know how much CO2 has been released by burning these fossil fuels. And that increase that we measure in the atmosphere corresponds to only roughly half of this fossil carbon that we have emitted through our chimneys and exhaust pipes. So there is no question that this increase might be partly natural. Rather, it's the opposite is the case. The natural Earth system has taken up about half of the fossil carbon that we have emitted. So now you might wonder, where is the other half that we have emitted into the atmosphere, but that's not there anymore? And the answer is simple. Most of this has gone into the ocean. The oceans soak up carbon dioxide because the concentration in the atmosphere has increased, so that there is now a concentration difference between the ocean waters and the air above it. And because the ocean and the air are in continuous gas exchange, they try to equilibrate their concentrations. So by increasing the concentration in the atmosphere, we automatically cause the ocean soaking up part of that CO2. And that on one hand is a good thing, because if the oceans didn't take up so much of our CO2, the atmospheric increase would be even faster, and we would have even less time to solve the climate problem. On the other hand, the CO2 absorbed by the ocean forms carbonic acid in the ocean water, and that makes the ocean waters more acidic. That is a problem that, if it continues for a few more decades, will start to impact marine ecosystems in a major way. So it really threatens the health of our oceans, because a lot of the organisms in our oceans form shells or structures made of calcium carbonate. And you can see that, for example, the coral reefs or the familiar seashells that we all know from the beach, or even more importantly, this microplankton that you see on the lower right, which is the base of many of the food webs in the ocean. And in fact, the ocean acidification is already now affecting oyster farmers in Canada. One of the major farming operators, aquaculture operators, is actually shifting business to Hawaii because the ocean waters are getting too acidic up north. So to me, as an ocean scientist, this problem alone is so big that it would warrant reducing our emissions as quickly as we can, our carbon dioxide emissions, even if CO2 didn't cause any climate change. But we know, of course, that CO2 also does cause climate change. I want to just quote a little historic reminder here. The famous German explorer Alexander von Humboldt already in 1843 wrote that humans are changing the climate by releasing large amounts of gas at the centers of industry. Now, at the time, of course, the greenhouse effect was already understood by Joseph Fourier in 1824, who had laid the foundations of all this. But Humboldt did not know which gases are actually enhancing the greenhouse effect and changing the climate in this way. That was only clarified in the year 1859 by the British scientist John Tyndall. He made the first series of measurements demonstrating which gases in the atmosphere cause the greenhouse effect. And he also delivered a beautiful, concise description of the greenhouse effect in 1859 when he wrote, "The atmosphere admits of the entrance of solar heat but checks its exit, and the result is a tendency to accumulate heat at the surface of the planet." That is a beautiful description that is still entirely valid today. This greenhouse effect caused by increasing CO2 was quantified for the first time by the Swedish Nobel laureate Svante Arrhenius in a famous paper where he found in the late 19th century that a doubling of the CO2 concentration would cause a global warming between 4 degrees and 6 degrees centigrade. That quantity, namely the temperature rise that results in equilibrium after a while from a doubling of CO2 concentration, that quantity is called the climate sensitivity, because it tells us how sensitively the climate reacts to a change in CO2 concentration, or more generally, a change in the radiation balance. The modern estimates of this climate sensitivity are a little bit lower than Arrhenius calculated over 100 years ago. Modern estimates are around 3 degrees centigrade for a CO2 doubling. Now, there is still some uncertainty attached to this due to a limited understanding of certain feedbacks, especially the feedback of clouds in our atmosphere. And the remaining uncertainty that we have is about plus or minus 1 degree centigrade. So we are very confident that the climate sensitivity is somewhere between 2 and 4 degrees centigrade for a doubling of CO2. Now, that climate sensitivity is really the key parameter that you need to know if you want to know how much will our emissions change the climate in future. Because if you know this climate sensitivity, you can immediately, at the back of the envelope, calculate, given a certain CO2 increase, how much warming you will get. And in this way, you can, for example, calculate that our emissions until this day, which have caused this 1.7 watts per square meter additional radiation forcing, that these should have caused a warming between 0.7 and 0.9 degrees centigrade until this day, if you assume a climate sensitivity of 3 degrees. Now, I said earlier that we have increased the CO2 concentration by 40%, and if the climate sensitivity is 3 degrees for a CO2 doubling, then you might wonder, why is the warming not 40% of those 3 degrees? There are basically 3 reasons for this. The first one is that CO2 is not the only climate forcing agent. There are other greenhouse gases that are also changing in concentration. There are also some cooling agents caused by humans, for example, aerosol pollution in our atmosphere. Now, as it happens, the sum of all these forcings caused by humans are about also 1.7 watts per square meter. So the cooling and the warming parts of the other agents roughly cancel, so that the total forcing is about the same as the CO2 only. But there is also, you have to take into account that the CO2 forcing is logarithmic with the concentration. So that's why 40% increase doesn't translate into 40% of the 3 degree warming. And another factor is that this climate sensitivity tells us the warming that is reached after some decades when the system has come into equilibrium. But in fact, the real climate system is lagging behind somewhat because the oceans delay the warming. They take quite a time to warm up, and this is called thermal inertia. And that you can either calculate from quite a simple climate model, or you can actually measure it because this thermal inertia is seen in the ocean temperature measurements. And in this way, you can easily factor that in. And when you do all this, then you end up at the prediction of 0.7 to 0.9 degrees centigrade warming that should have been caused by human activities until now. Now, if we look at the actual temperature measurements, we find that this is indeed the warming that we are seeing. So the human effect on climate is large enough to explain practically all the warming we observe. That's of course not a priori given, because there could be other natural factors influencing the climate in addition to human effects. If you look at the temperature, though, you see that there has been a warming about 0.8 degrees centigrade since the beginning of the 19th century. And of course that warming is not just steady, there are some oscillations around this trend. You can see quite clearly over the last 40 years or so that there are oscillations that are roughly about plus minus 0.1 degrees from year to year, and they have to do with things like volcanic eruptions like the Pinatubo eruption, or El Niño events in the Pacific Ocean, which periodically release heat there from the ocean waters. And 1998 El Niño was the largest event on record, and it sticks out, as you can see here, out of that long-term warming trend to some extent. But overall, there is a continued warming, ongoing warming within that corridor that we have observed now going on for several decades. We can, by the way, understand quite a substantial fraction of that year-to-year variability in the temperatures as well by doing simple correlation analysis, because we actually have independent measurements of the volcanic eruptions, the cooling effect of those, the El Niño events, and also the solar cycles. And by standard correlation techniques, you can work out how strongly these natural variations affect the global temperature, and then you can subtract those natural fluctuation components, and the result is shown here for the last 30 years. And here you see the 5 main series of global temperature that we have. The red and the orange ones are based on satellite data, and the other ones involve the surface measurements from weather stations around the world. And you can see that after correcting for these natural fluctuating parts, all 5 series agree very well within very small margins about the warming trend over the last decades. And you can also see that this is clearly a completely ongoing, unbroken warming trend. There is no sign of this warming slowing down, as you might sometimes have read in the media. Now we can also ask the question, how well does this agree with earlier projections? And here I show in the blue range the projection of the 3rd Ipcc report, and they started in 1990. The green range is the projections of the 4th Ipcc report. It was published in 2007, and these projections start in the year 2000. And the red line is the average of all these 5 global temperature series of the last slide, here shown at higher resolution, not just annual resolution, to emphasize more the kind of ups and downs in this. And you see that the warming that is actually observed is right in the middle of what was projected by the Ipcc in its last 2 reports. So there is no discrepancy here, and that's not very surprising, because we understand the Earth radiation balance well, and so the predictions of the global temperature change are quite robust, and they happen to be quite correct as well in the light of the data. I mentioned also that with the correlation analysis you can find out how strong the effect of solar cycles on global temperature, for example, is, and the result is that's an effect of about plus minus 0.04 degrees of the dominant solar change, which is an 11-year cycle, which has been known for centuries. And so it's really a very small effect compared to the greenhouse effect. And this diagram shows also how, just put together in one graph, how the global temperature curve and the measurements of the intensity of solar radiation received by satellites at the top of the atmosphere, how that compares. And you can see that these don't have much to do with each other. Basically, the changes in solar radiation are just this 11-year cycle with no sizable trend, neither up or down. And as it happens, actually the deepest and longest lasting solar minimum since the satellite measures began in the 1970s happened over the last few years and coincided with the warmest years in the global temperature. So there you have the faintest sun coinciding with the hottest temperatures, which clearly shows that the solar variability only plays a minor role here. If we did not have these temperature measurements, then in fact we would know that the planet is warming anyway, because you only need to look at our mountain glaciers. This photograph I took in New Zealand in the Southern Alps, and it shows the Müller Glacier coming into the picture here from the bottom right. And you can see the terminal moraine up to which this glacier stood about 100 years ago, up to the upper edge of that moraine. It's highlighted here with this white line, and you can see this glacier has really collapsed and formed a meltwater lake that is banked up behind that moraine. This is a picture that you can see all around the world in the mountain ranges. Everywhere, with very few exceptions, the glaciers are retreating quite massively. In the European Alps, they have lost more than half of their volume over the last 100 years. Now, if aliens were observing us from space, they would also know what's going on here. They just need to look at the ice cap on the Arctic Ocean here, the sea ice. They see the very bright white area. This is in 1979, when it was observed for the first time with this beautiful satellite view. And here it's in 2007. You can see it's shrunk by about 40% in that time period. If we go back once again and forward once again, you see how strongly the ice area on the Arctic Ocean has shrunk. And the next curve here, the red curve, shows you the whole time series of the extent of this ice area. And you can very clearly see this downward trend there. This slide also shows the Ipcc projections in this light blue range, and it shows that the actual loss of sea ice is happening much faster than expected by the Ipcc. I mentioned earlier that the temperature projections turned out to be pretty well right, and in fact already in the 1970s global warming was predicted in the major scientific journals Nature and Science, also approximately quantitatively correctly. That's because the Earth's energy budget is quite simple, but the behavior of ice is much more complex physically, and that's why the models can be quite wrong. And in this case, you can see that the models have really underestimated the problem. And unfortunately, as we will see in the next episode, a similar thing has happened with sea level rise. So sometimes you hear that maybe the Ipcc reports exaggerate things or are alarmist. I wish that were true. Unfortunately, the data show the opposite, namely that the Ipcc has really underestimated some major developments in the climate system. Now let us have a look into the future of the global temperature. I already pointed out that our activities, human activities, are now really dominating the changes in the Earth's radiation balance, and hence they are also the dominating cause of climate change. And that will continue into the future as well, unless some really extremely unexpected things happen, like a huge meteorite striking the Earth, or the sun doing something that it has never done in the last 1,000 years since we observe it. And so it is really, I think, pretty certain that the future is up to us, and that's why also we climate scientists, we don't predict the future. What we can do is we can calculate scenarios. That is, they offer a whole portfolio of possibilities that depend on human activities, on how much we will emit in the future. That is not something we try to predict. All we can do as climate scientists is tell society that if they emit a certain amount of carbon dioxide and other greenhouse gases, how much warming will this cause, including uncertainties. And that is what you see in this green and yellow and red scenario here. They are warming predictions or projections based on different assumptions about emissions. Relatively low emissions in the green scenario, they would lead to a warming somewhere between 2 and 3 degrees centigrade by the end of the century, or a more pessimistic assumption about how much we will emit, that would be the red one here, which leads to a warming between 4 degrees and 7 degrees. That would, by the way, be a completely different planet, because between 4 and 7 degrees, that happens to be the temperature difference between the last ice age and today. And certainly during the last ice age, it was a completely different planet. Now, these are the global average temperatures, and to finish off with, I would like to show you how this breaks down regionally. If you look at a climate model with a relatively high resolution, because of course what we experience as human beings is not a global average temperature. What we experience is a temperature at a certain location, and there are some major differences here. In this little movie animation, you can see the year running there. First you see only natural variability, which is basically weather, and of course the climate models also produce their own weather because the physics of all these processes is included. But after the turn of the century, the orange colors start to dominate, so the warming trend starts to dominate the natural variations. You can also see some hotspots of warming, like in the Himalayas or in the Arctic Ocean. Those are the regions where the snow and ice cover shrinks, and that's why you don't only get the warming due to greenhouse gases, but you get an additional warming because more solar heat is absorbed and less is reflected back into space. And finally, you can see quite clearly that the air above the oceans remains much cooler than the air above land. And that's very important, because if you hear about a scenario like this one, which is quite a moderate warming scenario with a global average warming of about 4 degrees, what it means on land is that in most areas it will be more than 6 degrees warming, and in some areas maybe even more than 10 degrees. And of course on land is where we grow our food, where we live, and so that is much more relevant to us than the global average temperature. With this, I will close the episode number 1. There are some further exercises for self-study presented in the following slides. And in the episode 2, I will talk more about the consequences of this global warming. Thank you.